Very good. Thanks for having me here. I'm really excited to share with you guys. I guess I'm the token machine learning person this morning, and I'll be talking about the challenges of machine learning at scale. So I've been working in machine learning for about 20 years now, and if you talked to me a couple of years ago, this is how I thought about machine learning. You start with some data, you run some kind of machine learning thing, then I show that my curve is better than your curve, and then I write a paper about it. And that's where it ended. And somehow, over the last few years, things have changed significantly. So I call 2015 the year of machine learning, because industries are being disrupted by intelligent applications. So these are things like Uber that completely destroyed the taxi business in the US. And the timing for machine learning is exceptional today. Companies have spent the last decade putting their data into one place, using tools like databases and so on, and not getting enough value out of that. So over the last few years, they've spent time and money on analytics tools like Hadoop that allows you to say things like, what fraction of my customers are churning? But they don't tell me why Danny is churning and what I can do to stop Danny from churning. And that's where machine learning comes in, that predictive power. So things like recommender systems, fraud detection, ad targeting, financial modeling, and personalized medicine are being completely transformed by the power of machine learning. It's an exciting time for it. So if you think about building machine learning systems, usually start with an idea. I call that inspiration. And you think that the first thing that you do is a mathematical model, but that's not the first thing that happens. Typically, you go and you clean your data, you do some transformations, you build some features, and then you bring in the machine learning piece, which I'm calling data intelligence here. And this is really an iterative piece. And finally, you bring these things to production because they impact your customers in real time. So the left side of the equation here is usually driven by people. And these folks typically use simple tools in a coffee shop with their laptop, so things like Python or R. There's a picture of a coffee shop back here. You can't quite see. And somehow, they have to take these things into production. And production usually happens with scalable, elastic systems, things in the Hadoop ecosystem. Nobody is creative inside of a Hadoop cluster. So the problem is, how do you go from that initial inspiration all the way to production? And there's three challenges along the way. Data engineering is painful. Nobody goes home to their wife and says, or their husbands and say, I had a great day today. I cleaned some data. And then after you've done that, going to the next step, the data intelligence piece can be hard. Building models at scale requires a deep amount of technology expertise and algorithms expertise. But then the last step, deploying to production, can be even harder. You have to build systems that are complex, interacting, and have little to do with the initial R or Python code that you built. So addressing these challenges requires you to think about two axes. One, simplicity, the second one, scalability. And today I'm going to talk about those axes in the context of these three areas. So let's start with data engineering. In terms of simplicity, we want simple tools for data cleaning and feature engineering. And we want to do those over terabytes of data. And these systems are mainly what's called data parallel, so they're typically easy to do. So for doing that, we need to focus on what I call scalable data representations. And let me tell you a little bit about the one that we use at the core of our system. And that one deals with how data is laid out. So typically, you think about data as rows. So let's say you have Netflix data. You can think about some data about users, movies, ratings, and so on. And this data might come as little pieces. They're distributed across machines. But data engineering and transformations usually don't happen in this way. When you're transforming data, you usually think about data in terms of columns. So for example, I'm going to show you some code on the left. Let's say I'm doing some feature engineering. The first thing I want to do is normalize my ratings data. So I'm going to take one column and divide it by its sum. Then maybe I'm going to create a new kind of feature. Maybe it's called rating squared. So that's creating a new column in the data. And maybe I'm going to select two of these columns, and I'm going to feed it to a particular machine learning algorithm. As you can see, most of these operations are about transforming columns and not rows of data. And that's why we've designed a scalable data structure called the SFrame, which allows you to deal with out of core, so it goes into disk, columnar representations of data. And it's highly optimized. and I'll show you a little bit about that. But the most exciting thing about it is that the same code that you write on your laptop in Python, even though the underlying layer is in C++, the same code distributes as this columnar representation distributes across machines. So SFrames are the core of our data structures, and they provide the scalability that we have. So if you compare, for example, to some of the standard tools in the big data ecosystem, on, for example, the sample task on Twitter data, this is a very large graph. It takes them quite a bit to process this data, while using SFrames, you can process it much faster. So this is 70 seconds as opposed to, say, 200 seconds with giraffe. But this is not the end of the story. These alternative methods are so slow that you have to use them on clusters. So here they're using a cluster of 16 machines, while the results I'm showing are on a single desktop. And our scalability, because of the data structures, have really impacted a wide range of problems. So for example, if you take the common Craw, which is a large web graph, which has 128 billion edges, this is the large web graph available today in open source. The folks at Common Craw tried to analyze this graph of a wide range of systems, and basically nothing scaled. And then they took a desktop, actually it was an Amazon EC2 machine, with an SSD, and they ran it on GraphLab Create, our system, and they can iterate over it in about 9 minutes, which was pretty exciting for them. So at the first part, what we talked about were data structures that allow you to scale to really large data sets with simple tools. Let me talk a little bit about the data intelligence piece. These are machine learning tools that allow you to provide machine learning for non-experts. This is what Ron was talking about in the previous talk. And here you don't measure your data in terms of terabytes, although people are obsessed about how many terabytes or petabytes they have. Here you think about the computation-intensive algorithms that allow you to deal with that data. And these tasks are much harder. They're not data parallel. So you need smarter algorithms. And in this piece, we've been thinking about robust machine learning algorithms that scale to much larger data sets. And at this front, as Ron was talking about, we think about a hierarchy of types of users. At the very bottom, you have data scientists who think about algorithms and writing their own over an SDK, while some savvy developers might think about machine learning tasks like regression, classification, and clustering, while business users or other developers might think about higher-level business tasks, like how do I build a recommender system, or how do I target to my users. And so you need machine learning algorithms at different levels of abstractions that allow you to start from a simple black box and then open it up and tailor to whatever application you have. And this is what we've done with a wide variety of settings. So let me show you an example of one. So this is my first live demo. Hopefully it works. So here we've taken 1.5 million images and built a deep learning model. So this is a neural network that predicts with 1,000 different classes. And so every time you click on an image, it gets sent to a server that has a GPU. There was a bit of talk about GPU earlier, so our stuff runs on GPUs as well. It goes through that neural network and makes a prediction as to what that image is. So for example, for the image here on the left, the prediction is, let me just enter full screen here. The prediction is snail, which turns out to be true. Let me click on another image. Some of this might appreciate this one, for example. The connection is a little slow, but it gets uploaded, if internet works, to a AWS machine, which has a GPU. It goes through that model, comes back for prediction. In this case, it says beer bottles. Yeah. How about this one here? Let's see, mask. That made sense. This one looks a little trickier. Let's see, harp. That's pretty impressive. Now, these are all images in the original data set, so it's a little bit of cheating. Let me show you an image that was not in the original data set. So this one over here gets sent to the AWS machine, goes to the GPU, comes back for prediction. It says Labrador Retriever. This is my dog. This is the lab in GraphLab, for those familiar with it. Now, let me tell you about how this is an example of making machine learning more accessible. So last year in October, we released 1.0 version of our system. And a week before, a new front-end developer, Dick, joined our team. And Dick comes in on a Monday and says, what should I do? And we're all busy with 1.0. So he said, why don't you play with the product and build something? He had never done machine learning before. He didn't know anything about our product. He built this in a few days. So I find that really exciting. So that's pushing at the middle and top layers of this hierarchy. Now, again, I talked about usability or simplicity. We can also talk about scalability. So, for example, the deep learning model that I showed you is extremely fast. So if you compare it to some of the existing systems, for example, H2O's implementation on 63 machines, they process about 23,000 images per second. Actually, this is per minute. But anyway, they process at a certain rate. Us, with a single GPU, we're quite a bit faster than 63 machines. So as we discussed, we want to make machine learning accessible to non-experts. And here we're talking about complex models that need to be scaled up. Now, the last piece of the puzzle is about deployment. So how do you deploy the systems such that every time I click on an image on my laptop, it gets shipped to a machine that goes through a prediction and comes back in real time and gives me an answer? So this is not about terabytes of data, and this is not about the complexity of the model necessarily, but this is about how many predictions you can make per second, and how it can be robust to failures in the underlying system. So this is where the predictive piece comes in. How do you deploy these predictive systems in production? So let's talk about what machine learning deployment looks like typically. So I typically start with data, and I run some machine learning algorithm, because I'm a data scientist. But if I want to deploy it, I have to talk to other people in the organization. It's hard. I have to walk over to their building. These are typically data engineers or architects. They don't understand what I'm doing. It's a long, slow process, which can take 6 to 12 months. And the system that's eventually implemented is irrelevant because the world has changed. Or maybe because Google came up with a better solution. These two teams have to maintain two systems in a slow, deliberate way. And so to avoid that, we've been thinking a lot, as Ben said this morning, we've been thinking a lot about what it takes. Is that a question? No. Sorry. I've been thinking a lot about what it takes to deploy these models in production. So from an app developer perspective, you should also always think about how do my users interact with my application in real time. And as a data scientist, you're usually isolated from these folks. And you think about your machine learning models. And the question is, how do you connect the two? And so with predictive services, what we've done is build a robust, scalable system where your machine learning model in one line of code can be deployed as a scalable service. So every time a user comes to your website and you want to query the recommender system, that query gets passed through a caching layer to this predictive service that hosts a model, and it comes back with a prediction. This is some products this user might want to buy. And these products can be then shown to the user. Now, if some new data arrives, or you come up with a new, fancier model, you can deploy it with no downtime, which is very exciting. And these predictive services allow you to deploy GraphLab Create models, which I've been talking about, but also scikit-learn models, or any Python, or basically anything that you build. So we've been building this generic layer to support machine learning in production. So let me show you a quick demo of that. So this is demo number 2. So we took a large data set of Amazon reviews and built a recommender from it. So for example, let's say that I love the movie Dumb and Dumber. Yes. So if you love the movie Dumb and Dumber, if I click on that, it gets sent to a service that has predictive services on Amazon EC2, and it comes back with a prediction, usually milliseconds, but the internet is a little slow here. And it says, you should watch some other stupid movies with Jim Carrey, Adam Sandler, and so on. So all that makes sense. But you've seen recommenders like this. Let me show you something that you probably have not seen before. Let's say that I love the movie Dumb and Dumber, but my wife really wants me to read the book Sense and Sensibility. And we're having relationship problems. and we can't really afford to go to a therapist. And so can we use a computer to help us solve this problem? So the question here is, if you imagine the space of all products, and you build a graph where two products connected together if lots of people like both products, the question is, what is the shortest path between my preferences, Dumb and Dumber, and my wife's preferences, Sense and Sensibility? So I provide this two endpoints. It gets sent to AWS, goes for a predictive service, which comes back for shortest path, which is shown in the bottom. So watch Dumb and Dumber. Then you watch a stupid movie with Adam Sandler, but he's also in romantic comedies, so maybe you'll watch The Wedding Singer. Then you watch another romantic comedy called Clueless, which you may not know, but it's a parody of Emma, which is a romantic comedy based on a Jane Austen book. So you're ready to watch another romantic comedy like that. You read a Jane Austen book, and you're finally ready to read Sense and Sensibility. And this is how we solve relationship problems. So if I had a few more minutes, I'll give you a live demo of how to easily build a few lines of code, a system like this, and deploy it in production. But I will skip that and just conclude. Actually, according to my clock, I have 4 minutes. Maybe I'll buy those. Should I do the detailed demo? I'll stay. OK. So just a summary of what we've been thinking about. We have this open source, highly scalable data structures, the SFrame and the SGraph, which allow you to deal with lots of data out of core and help with the processes of data engineering. And on top of that, we built GraphLab Create, which provides advanced machine learning tools as well as data visualization tools to allow you to build those applications very easily. Now, when you want to deploy them, there's two modes of deployment. You want to deal with more data. You want to distribute it, you can use data distributed, which runs on the cloud or on-premise using a Yarn cluster, so on Hadoop. Or you can deploy as a service that can be queried in real time. This is where data predictive services comes in. And that's the demo I just showed you. So in summary, the world is changing significantly because of machine learning. Industries are being created, disrupting other industries. And building intelligent applications from that original inspiration all the way to production is one of the key challenges of today's economies. And for that, we need to address the problems in data engineering, data intelligence, and deployment. Thank you.